This is essentially a delta function, a vertical thing. Okay. The same thing is going to be true when we have more than two bins. Okay. So our problem is going to be greatly simplified here when we realize we don't have to think about every possible distribution. That's huge. All we need to think about is the most probable distribution. Okay. When we go from the microscopic to the macroscopic, we don't. The most probable distribution so overwhelms all the others, we don't have to think about them. This works at the macroscopic scale. In intermediate scales, 100 objects or 10,000 objects, maybe you have to worry about more distributions. But if you're talking about Avogadro's number of systems, you really only have to think about one distribution, and that's the most probable one. So we're going to label the most probable one as with a star or asterisk. Most probable. And so this goes to, as we go to macroscopic size, in the limit of huge, if you like. In the limit as you get big, if you like, this becomes so we get rid of the sums because the only term of the sum we need to think about is, so the sum here was over all distributions, by the way. The sum is over all possible distributions. Where'd my purple go? The sum is over all possible distributions. And so what we're saying is we can ignore every term in this sum except the most probable distribution. That's with the asterisk. So we get rid of the sums. What this means is the number of systems in state J for the most probable distribution. So that's cool. So this is real important. This step right here is like the second. We've encountered three important things. One was the principle of equal a priori probabilities. The second is the ensemble approach to thinking about the problem. And the third is replacing the sum with the most important term. Those are the three important things we've done, conceptual things. I want to introduce you to a word. Can you remember the word? Ansatz. Ansatz.
You're the one who keep telling it to me, and I remember.
Anybody know the word Ansatz? It's a German word, and I speak German, so I like it. But it's actually, for scientists, an important word. It means approach, the basic conceptual approach to something. That's our Ansatz. That's how we start. That's how we begin. So here our Ansatz is the ensemble. Think about the ensemble. So you can think of Ansatz as approach. It's a German word, but it's used internationally, so you'll encounter it. That's what I mentioned. Okay, so we've done those three things. And, we get them. So, our problem becomes, quite simply, to figure out which of these distributions W, A, gives us the maximum W, right? So our problem is to maximize W. You got a map? We went to So we're going to find A star by maximizing, and W star by maximizing W. So, what approach do you think we use? Well, it's the tip of everybody's tongue, I know. The Lagrange approach to find the maximum in a function. W is just a function of all the A's. So we simply want to maximize W. Maximize W subject to constraints. What are the constraints? The sum of the little aj's is capital A, which you can think of as a constant. If you like, you can rewrite this. Last class we wrote constraints as something equals 0, g of something equals 0, so you can rewrite the constraint this way, it doesn't matter. And the other constraint is, and if you like to rewrite it, you can. So, then, according to the Lagrange idea, this becomes a set of equations. Let's see. What, it turns out, yeah, we want to maximize W, but it just turns out to be easier to maximize log W. So we're actually going to maximize the logarithm of W. Okay. Doesn't matter. The maximum of W occurs at for the same distribution as the maximum of log W. Just it's more convenient. So we're actually going to maximize this log W with this set of equations. Okay, that's really a set of equations. Now this is not quite the way the book writes it. These are the undetermined multipliers, lambda 1 and lambda 2. What the book uses, and it's the usual thing, alpha for lambda 1 and a beta for lambda 2. Also note the partial derivative of each of these constants will be 0, so you can just write the equation without the constants, and it's still the same problem. So this becomes that's our problem. Yeah. So since this is just a set of equations, so then we have to solve so that's what we have to do. So when we take this partial derivative, we get yeah. So then we have to substitute for W. So now we see that we can, this is simply some calculus that we can do, just taking derivatives, right? The dependency here is in the denominator. So that's really all there is to do it. This is going to be simple. This is a sum, and the only term in the sum that will remain is the one for a sub j. So this will simply give you alpha, right? And this one will just give you, so it'll be minus alpha. This will just give you minus beta e sub j when you take the derivative. And this becomes the only tricky part. And here's where we'll use Stirling's approximation. Remember, this is the log of the prime minus the sum of all the little a's, right? In terms of the sum of the logs, right? And the derivative of this is just going to be 0 because that's a constant. So all you really need to think about is that. So use Stirling's approximation for this sum. So this would be a log a minus a minus that's what you have. So when you take this derivative, what remains is once you do the math, and you can do the math on your own, this is what you get. We can rearrange this by, we want to solve for a sub j, not log of a sub j. By the way, this will be a sub j for the maximum in W, so I can use the asterisk here to represent the maximum. So this becomes then so that's cool, right? So that's our a sub star j, and you can do this for any j in the distribution. So you've got the whole maximum distribution defined. Okay. What remains to be done is to figure out the values of the undetermined multipliers alpha and beta. And we'll find alpha and beta by applying the constraints that we already set up. And these are the two constraints. Now this is actually pretty convenient because I really should have left this here, but you can still see it. Isn't that nice? The probabilities, yeah. So step one is going to be to apply the first constraint. The sum of all the a sub j's is equal to a. Now this will be true for any distribution, right? And in particular, it'll be true for the maximum distribution. So I can add that asterisk with no problem. So what we have then is that So in principle, then, we can solve for this. So that's cool. We could solve for alpha by taking logarithms. We don't actually need to solve for alpha for our purposes. We can leave it that way. Substituting that back into here, yeah, gives us that now remember, a while ago, what we wanted to know was the average value of a particular occupation number across all distributions. We needed to know that. So now we can do that because the average value of this is going to be equal to the only distribution that matters is the maximum distribution. So in this average, we can replace this average by the maximum value of A, little a. And this is, of course, equal to our P sub j, the probability that we're in state J. Probability that a system is in state J. So from here, we can see that the probability is just this thing minus the A, without the A present. So this is a very important result. We've just almost derived the Boltzmann distribution. Right? Remember, if you think of Boltzmann distribution as an exponential distribution. So we have exponential of minus beta times the energy divided by the sum over the exponential of minus beta, all energies. That's a Boltzmann distribution. So we just derived the Boltzmann distribution from first principles using the ensemble ansatz with the equal a priori probability, with the postulate of equal a priori probability. So it's really all we've done. No other postulates, and we've got the Boltzmann distribution. Of course, what remains is to discover beta. Okay. The second of the undetermined multipliers. Do we have time to do that? We've got about 10 minutes, right? I think that's what we'll do. So let me tell you how, I'm not sure we'll get through it all, but I think we ought to start, because that would make a nice complete approach here. So we want to get at beta, and we're going to do so by applying the second constraint, which is really this. Okay. And the way we're going to get at beta is not going to be quite as satisfying as the way we got at alpha, but I think it'll still be convincing. We're going to consider a particular thermodynamic equation that you'll recognize. And then we're going to calculate a couple of average properties and find an analogous statistical thermodynamical, a statistical mechanical expression, and by analogy between the two, we'll conclude what beta must be. Okay. So let me first tell you what we're talking about. Now this is a thermodynamic expression. You may not recognize it, but you can easily derive it. And in fact, one of the problems in the book is deriving this from first principles, and I put that on the assignment. It's problem 1-29. It's out of chapter 1. But let me remind you, this book uses old nomenclature. You may have noticed it was written some time ago. So this book uses E for the internal energy. Nowadays, the common term is U. So when you took thermodynamics, probably you saw U instead of E. Nowadays, we reserve E often for the quantum mechanical energy and U for the internal energy, or E for a general kind of energy, but U for the specific internal energy. Here, E represents the internal energy. So you may recall that du is equal to TdS minus PdV, or this is dE, plus mu dN, where mu is the chemical potential. So just to remind you then, so T is the we call, therefore, S, V, and N the natural variables for the internal energy. If you think back to thermodynamics, N is a convenient thing, may not be a convenient thing to control. V is fairly simple to control. You just use a rigid container. S is hard to control. Temperature is easier to control. So internal energy is not the most useful state function. Gibbs free energy is more useful because there the natural variables are T, P, and U. But for the internal energy, it's S, V, and N. So I wanted to remind you of these partial derivative relationships. And from these kinds of relationships, and remembering the relationships between partial derivatives and changing variables, you can derive this. Okay, so I won't do that here, but it's a nice exercise to remind yourself of those. It's going to be more convenient to use a different form of this. So we're converting from temperature to inverse temperature as our variable, and that's what we're going to then be using. You'll notice that I've not made reference to S, instead I've made reference to T. Okay. So this is the thermodynamic equation we're going to make reference to, and what we're going to do is calculate, so this is our reference, our thermodynamic reference, and what we want to do is calculate some averages. And from those averages, we'll then construct, notice this is a partial of E with respect to V, and a partial of P with respect to inverse temperature. So we're going to construct some averages from our statistical mechanical equations and develop a relationship analogous to this. That's what we're going to do. Now, if we go back, let's see, here. This sum occurs over and over in statistical thermodynamics, and therefore it has its own name. Its name is its own symbol and name. The symbol we use for it is Q, and it's called a partition function. Now, you'll see as we go along that different ensembles have slightly different natural partition functions. This happens to be the canonical ensemble. So we call this the canonical partition function, Q. So Q is the sum. And the name sounds funny, I know, partition function. What's that mean? But you can think of it this way. You can think of the partition function as representing the way that energy is partitioned among the different accessible states of the system. And we see that energy is not, in fact, partitioned equally among all states. It's partitioned according to an exponential. So partition function is quite fundamental to everything we do. So here's a curious thing. E sub j, if we think about what it depends on, E sub j is going to depend on the number of particles in the system and the volume of the system. Right? That's really all it depends on. The average, though, well, let's say Q. Q, on the other hand, depends on, again, on N and V, but it also depends on this thing beta. So what we're going to find out is that the average energy is going to come from Q, and it will have this dependency on N and V and beta, while the individual energies depend only on N and V. Okay. So I think we'll have to continue next time, but what we're going to assume, and this will be a postulate, is that the thermodynamic energy E is the average quantum mechanical energy, where the average is taken in this Boltzmann-Noether way. Okay. So this is another postulate. Our postulate is that the thermodynamic energy is the average energy calculated in the statistical mechanical way based on the Gibbs ensemble ansatz with the assumption of equal a priori probability. Okay. And likewise, so we're going to calculate the average energy. And this is going to be true for any property. So we're going to calculate an average pressure, and our assumption is that the thermodynamic pressure is equivalent to the average pressure calculated with our Boltzmann distribution on ansatz.
Why no temperature? Because the temperature in the partition function is the same as each individual system. So I would think the energy would need to depend on temperature as well.
And we will find that beta and temperature are intimately related. Beta is a function of temperature, or really beta is the more fundamental thing. Beta is just this undetermined multiplier that comes out from, that is determined by maximizing W. So really beta is the more fundamental property, and temperature, we'll see, is proportional to beta. And you can choose any, the temperature, any temperature scale you choose is arbitrary, you know. So depending on your temperature scale, you have a different proportionality. But temperature and beta are roughly the same thing. So what we're doing is we're coming up with a definition of temperature from first principles.
You said J depends on N and V because we're just treating the particles as particles in a box,
Yeah,
right?
so we're talking about a system here with some number of particles in here. E sub j represents the energy level or the state of the whole system. And we know for a particle in a box that the energy levels accessible depend on the volume via the dimensions. And if you have one particle in a box, that's all that it matters, all that matters. But if you have several particles in a box, then the number of particles also matters. Okay. So N and V. And that's all that's needed to determine the energy levels of the system. But to determine the average energy, you also need to know the betas, which turned out to be temperatures. So that's where we'll pick up actually tomorrow morning, but not quite certain. So is that clear?